So let's start with the first part, where we will cover topics like what modal analysis is. Then I will show you where modal analysis is used, then how to perform modal test and modal analysis and what is the difference between those two. I will present you the new model geometry that was just released in the Devesoft X 2021.3. And then I will also show you an example on a data file. So what's modal analysis? Modal analysis is a process of extracting modal parameters. And these modal parameters are natural frequencies, damping factors, and mode shapes. So it's basically a study of dynamic properties of the system in the frequency domain. And it is an indispensable tool in understanding how structures vibrate and how resistant they are to applied forces. It is based on the structural test measurement or simulated finite element models and allows machines and structures to be tested and optimized. Where should we use modal analysis? So it's really used in all kinds of applications, from automotive industry, aerospace, civil engineering, power, and also more fun topics like musical instruments or sports equipment and so on. Why do the customers need to use modal analysis? So a lot of problems can come due to the product optimization when they are trying to reduce weight, increase efficiency, and they need to validate all the changes and make sure that they are compliant with standards or with the intended use of the product. So if you go into each application more deeply, where modal analysis is used. So for example, it's used on the car frames. So the customer places accelerometers all around the car frame, excites it with a shaker, and then takes a look at how the structure behaves. Then we can test each car component individually, from suspensions, exhausts, brake discs. On the other hand, they can also test engines and at the end, fully equipped car. So then if we go into the aerospace and defense, one of the most known tests is the ground vibration testing that is done on the aircraft. And this is a large structure. Then also individual components can be tested, like landing gears or wings and so on. Also here, the engines can be tested, and modal analysis is also used for flutter testing, which is one of the most common phenomena that exists in aerospace industry. If we go to construction and civil industry, we can find a lot of different areas where we use modal analysis on pumps, compressors, in addition also with order tracking, torque vibration. Then we can test wind turbines, bridges, and so on. And also in, let's say, washing machines need to be tested, loudspeakers and musical instruments. For example, we have a customer that is testing the gramophone like shown on the picture on the slides. So what do we need to perform modal test and analysis? So at the beginning we need an exciter to excite the structure. And this can be a modal shaker or an impact hammer. This depends on our application. So we need to take into account what kind of structure we are testing, what is the frequency range, and so on. So it really depends on the application. We need force transducers that will acquire this excitation signal. On the other hand, we need accelerometers that would acquire the response signals from the structure. Of course, we need a data acquisition device to display and record the test. For example, Sirius, DV43, if you have a large channel count, you can use the R4, R8 or HD series, so it's up to the number of channels that you want to use. And then of course this device needs to be connected to a computer that has the capabilities to analyze the results, like Devesoft X, for example. So how is modal analysis performed? So there have been a lot of questions, what's the difference between modal test and modal analysis? So basically, modal test is measurement procedure. So to do the modal test, we need to know what kind of structure we are measuring, we need to prepare the equipment that we are using, we need to know what kind of excitation technique we will use, the configuration, the geometry. When we do the measurement, we get the frequency response function and also the coherence that is able to validate our measurement. On the other hand, we have the modal analysis, which is analysis of modal test data. And in this modal analysis module, we indicate parameters, modal parameters, with the help of mode indicator function, curve fitting algorithms, stabilization diagram, and so on. And to validate the model, we use the AutoMech and the FRF synthesis. So grayed out is also comparison with finite element model and also the cross-Mech matrix, which is currently not supported in Devesoft, but we will add this also in the future. So let's briefly take a look at the modal test. The modal test is the base for performing modal analysis and to even make some conclusions on the structural dynamics of test object. In Devesoft, we support experimental modal analysis where objects are excited by artificial forces, and we measure both excitation signals and response signals. And we support a lot of different configurations, from single input, single output, to single input, multiple output, and also multiple input, multiple output configurations. If we focus now a little bit more to the multiple input, multiple output configuration, for that kind of test, we usually use more shakers to excite the structure, and also more accelerometers to cover the whole structure. And the advantage of using multiple shaker is that the input force energy is distributed over more locations on the structure. So this is especially helpful when we have a large or complex structures and with heavy damping. What is the result? What are the results from modal tests? So, of course, the first one and maybe the most important one is the frequency response function, also called FRF. And this tells us the ratio between the output response motion and the input excitation force. And what we get is the curve that you see on the picture. And we can tell that at high frequencies, with high FRF magnitude, we can tell that the structure is more sensitive and the output response will be relatively high, even at low input force levels. The FRF is a complex vector, so we have an information about the amplitude, phase, real and imaginary part. The second function is the coherence, and this is also one important parameter when we are trying to validate if our measurement was successful or not. The coherence is a number between 0 and 1, and it tells us how good our output spectrum is related to the input spectrum. So it shows us how good our measurement is, basically. So if the coherence is 1, the measured response is caused totally by the input power. And if the coherence is less than 1, it might indicate some noise in our measurement, or we need to repeat the measurement to excite also this frequencies. The geometry, of course, the results from modal test can also be animated, and in the latest release we just released the new modal geometry version, where we support creation of objects like cylinder, sphere, cube, and so on. So the creation of objects is much more easier, and therefore we can create more complex shapes much faster. We also implemented advanced interpolation of non-measured points together with color animation. So at the previous versions we could only animate the points that we actually measured, and now we also implemented the interpolation. So you just need to connect the unmeasured point with the measured point with the line, and also the unmeasured point will be animating. We also implemented the possibility to show the non-deflected shape together with the deflected shape. So I will show you a data file of the measurement. So let me describe a little bit this measurement. So we conducted the measurement on a demo airplane, where the structure was excited with 2 shakers, and the excitation was measured with 2 force transducers. The response, we placed 6 accelerometers all over the structure, as you can see it on the picture, and we measured response at 6 different points. So all the sensors were connected to Sirius HD, and we used Devesoft modal test to have the data. So let's take a look at how the modal test setup looks like. So in the modal test we selected shaker as the test method, we defined the resolution, and the excitation source was selected as our own analog out function generator. We excited with the burst random signal, and we set the excitation duration to 30%. That means that the 30% of time of defined segment the structure will be excited, and the other 70% the structure will vibrate freely. So we defined 2 excitation channels, both of them were force sensors, and we defined several response channels. Some of them were 3-axle accelerometers, and some of them were uniaxial. So when we take a look at also the signals, you can see the burst random signal, time domain signals. So the structure was excited from Devesoft analog out, and we measured the responses. When we take a look at the model test data, like I mentioned before, we have the frequency response function, and at the peaks there might be an indication of a resonant frequency. The second graph tells us, shows us the coherence, or how well our excitation was related to our response channels. You can see that the structure is already moving when we are trying to animate each frequency individually. Okay, so these are the capabilities of modal tests. So it's basically meant for a brief analysis of our data and animation. If we want to go a step further, we need to have modal analysis module. And so this is the next step from acquiring the model test data. And in model test, we use different curve filters and mode indicator functions in order to identify model parameters. Like I said, we do the modal parameter estimation with the help of mode indicator function that helps us identifying how many modes there are in our measured data. Then we have also the stabilization diagram that helps to identify stable poles. The poles are stable in frequency and in damping. And the user must select these poles. I will show you also the demo later. And then we have the curve fitting, which is the main process in modal parameter estimation, where model parameters such as natural frequencies, damping coefficients, and mode shapes get extracted from measurement data. In Devesoft, we calculate one of the parameters that we calculate in modal analysis module is the complex mode indicator function. So each degree of freedom has its own complex mode indicator function, and this is the advantage of the function, that it can detect closely coupled modes with repeated roots. It is based on the singular value decomposition, and it is used to identify all the modes that are included in the model test. So the complex mode indicator function shows us where in the frequency spectrum the resonances are. Then the complex mode indicator function, together with the results of LSCF algorithm, are shown on the stabilization diagram that helps us to identify stable poles. And these poles consist of modal frequency and damping. After we acquire this data, we need to make a model validation. And this is the next step after the model parameter estimation process is completed. This validation usually includes the MAC inspection and also FRF synthesis for comparison with real measured FRF data. So in Devesoft, we calculate so-called AutoMAC matrix. And AutoMAC is a procedure that can be used to validate the accuracy of models. It's basically a measure of similarity between estimated mode shape vectors from the same parameter estimation. So it is a good tool when you are trying to see if you measured at enough points so that you avoid spatial aliasing. The next step is the FRF synthesis that is used as a validation tool by comparing the FRFs that were measured with the synthesized one that are synthesized from the estimated model. And from this comparison, it is possible to see how well the estimated model mimics the dynamics of the actual physical structure. So yeah, let's go back to our data file to analyze it. So from modal test, we go to modal analysis module. And when we click add all transfer functions, all the transfer functions that are calculated inside model test are automatically recognized by modal analysis. If we want to take a closer look how they look like, we have a dedicated tab, transfer function preview. So for each transfer function, we can take a look how it looks like, and also with this preview, we can determine the appropriate frequency range for our structure. We also have the possibility to make a damping correction, and this damping correction is used when we are using exponential window during the model test measurement. We did not in this case, so I will not use the damping correction. Under the calculations, all the parameters that I described in my presentation are calculated. So, complex mode indicator function, we do the FRF synthesis, we show the mode shapes, and also the AutoMAC matrix. So when we go to review, I go to model analysis screen, and recalculate the data. So, on the stabilization diagram, I see the complex mode indicator function together with these green circles that indicate stable poles. So what does it really tell us, these green circles? So on the right side, I have the order of polynomial that is used to curve fit the data. So, and these green circles shows us which pole is stable at a certain order. Then it is up to the user to select these poles. If they are too closely spaced modes, you can easily zoom into the region to select it. When you're done selecting your poles, you just click recalculate button and you can already see the results. The stabilization diagram can show the order or the damping. A lot of engineers like this view, especially to see the damping of the certain peak in the frequency domain. So on the right side we have a table with the mode ID that we just selected in the stabilization diagram, together with the frequency and the damping ratio. On the 3D graph we show the automech matrix, and this basically tells us how my modes are similar to each other. If we go to the mode shape animation, we also implemented in the new geometry very easy mode. So we just go from single geometry to mode shapes, and automatically all the modes are animating. I can also change the number of columns. So all the modes that I selected previously in the stabilization diagram are shown also as the animation of my structure. If we go to the next section, so we covered the complex mode indicator function, automech matrix, and the next is FRF synthesis. So I prepared a couple of 2D graphs where we compare measured FRF data with synthesized FRF data. So let's make an experiment where I will show you how this works. So let's go, let's add a stabilization diagram, and now we will observe what is happening with the synthesized FRFs when I select or unselect a mode. So if I unselect a couple of modes, you can also see how the green curves in the background are not interpolated, are not fitted. And the synthesized FRF looks a lot different than what I actually measured. And when I click on all the peaks in the complex mode indicator function, I can see how well the FRFs are fitted to the measured data. So what will be the next step in modal analysis is also to implement the comparison between measured data with finite element model. So this will be the next step. Okay, so with that I would conclude the first part of the presentation and demo, and now it's time for your questions.